So now that we've worked through some basic applications of dot products, we need one more big application before we head out to cross products. And that is the orthogonal projection. It's a measure of how much one vector points in the direction of another. So we set the stage for this a little bit when we looked at this particular force and distance diagram. We were particularly interested in the force that's parallel to the distance vector. That's the part of the component of the force vector that matters to us. And we found it by the magnitude of the force times the cosine of the angle, because of course this is forming a triangle whose hypotenuse is the magnitude of that force vector. So we're going to use that idea and we're going to kick it up a notch. So we can think of an orthogonal projection of u onto v as the vector with its tip at the point where a perpendicular dropped from u to a line through v would intersect that line. So in other words, if you look at the diagram here, you have u here and you have v down here, or the line that contains v. And the shadow that it would drop from a perpendicular is the projection. See, there's a perpendicular line right there for the shadow. And that's how we think of these. We think of them as the shadow that u casts upon v. Assuming, of course, that the light source is perpendicular, because that's part of that assumption. All right, so we denote this, and you can see it right there in the diagram, with the projection of u onto v. So that's the way we note it. The vector projection is the projection of u onto v. Now the length of that projection is called the scalar projection. So how long it is called the scalar projection, and that's denoted with the scalar. All right, and you'll note that if it's casting onto positive v, if it's going in that direction, then it would be a positive value, right? So if it's onto v, it's a positive value. And if it's onto negative v, then it would be negative. Right? Let me do that in a different color. So here, negative v would make it negative. All right, so let's look at some basic examples here. Okay, we're going to draw the projection of u onto v, and then we're going to find that projection, and we're going to find the scalar. So we got a lot of work cut out for us. Okay, so we have 4, 2, and 6, 0. Okay, so 6, 0 is down here. That's v, right there. And then we have 4, 2, which I'll draw in pink, over 4 up 2, so that way it matches the diagram on the previous page. And that's u. Now you imagine a perpendicular light source. It would drop down and create the projection of u onto v. So it's drawn. I drew it. Now what is that projection? Well, that projection is a vector into its own right. So the projection of u onto v would be the vector that is 4, 0. And we know the magnitude of that, which would be the scalar. The scalar of u onto v would be 4. Right? It's the magnitude of this. So square root of 4 squared plus 0 squared, which is 4. All right, let's do another one. So we're going to put negative 2, 3 onto 4, 0. Okay, so we have 4, 0, which is right here, over 4 up 0. And we're going to put negative 2, 3 onto that. But negative 2, 3 doesn't go onto that. So negative 2, 3 goes onto negative v. Right, so over here, this is v. Let me do it in a different color. Just thinking about my color choices here. How about purple? So there's negative v. And that's where negative 2, 3 is going to be on. Now if I drop the perpendicular, imagine the light source up above, and I drop the perpendicular straight down, it'll be negative 2, 0. So the projection of u onto v is negative 2, 0. All right, now the scalar is going to be negative. Now, normally the magnitude of a vector, oh, I should draw that vector, sorry. That projection vector is right here. It's that piece. Sorry, I didn't draw it. I have to draw it. So the scalar is normally positive, right? So scalars, or excuse me, the magnitude is normally positive, but not in this case. So in this case, because it's going on to the negative v, we're actually going to make it negative. The square root of negative 2 squared plus 0 squared, which would be negative 2. So at this point, you have to remember what it said on the previous page, which is that it's a directed length. So it's not just the magnitude. It can have direction. And the directions are either positive if it's going with the v, or negative if it's going with negative v. In this case, it's going with negative v. So that makes it negative 2. All right, now we're going to take 3, 4, and we're going to project it onto 0, 2. So we're going to go vertical this time. So 0, 2 is right here. And we're going to take 3, 4. So over 3, up 4, which is right here. Now remember, it's not necessarily onto v. It's onto the line that contains v. In this case, it's longer. And you have to imagine the light source is coming from this direction, because the light source is always perpendicular to the v. So in these two, because v was horizontal, my light source is coming straight down. So if you want to imagine, that's the light, right? So your light source is pointing downward. But on this one, because v is vertical, my light source will be pointing towards it, like that. Okay, so then what's the projection? Well, dropping a perpendicular, my projection will be right there. So the projection of u onto v is over 0 up 4. And since that's positive v, that means my scalar will be positive. So here's the vector, and the scalar of u onto v will be the square root of 0 squared plus 4 squared, which is 4. All right, so far we've done horizontal and vertical, right? But what if it's on a diagonal? What if our vector v is 2, 2? Right, so there's vector v right there. Ooh, I should have labeled that over here. And this is vector u. Okay, so I didn't label the top one either. All right, so what if I'm going negative 1, negative 3? Negative 1, 1, 2, 3, which is right down here. Okay, so my projection going straight at it would actually be going in this direction, right? So along the diagonal. So I'm going to be going that way, because your light source has to be perpendicular to the line that contains v. So your light source is going that way. So your shadow is right here. So again, we're on to negative v, like that. But it's a diagonal line, right? I know how this is going to work, right? So it's going to cast that shadow back that direction. It's a little hard to see because I drew this in such a big marker, but what's happening is it's hitting at negative 2, negative 2. So the projection of u onto v would be negative 2, comma, negative 2. All right, so then the scalar would be the size of that, which would be the square root of negative 2 squared plus negative 2 squared, which would be the square root of 8, which is 2 square root of 2. Oh, and since it's on to the negative direction, we're actually going to have to put a negative in front of that. So it's negative 2 square root of 2. Okay, well, it's rather obvious this is not the way we want to be doing this. We want a formula that will give all these values to us. So that's what we're going to develop on this page. So we need a way to find the projection of u onto v and the scalar. in a way that's going to work nicely and not give us lots and lots of grief. Okay, so we have u right here. The magnitude of u, right, there's our u vector. And then we have our v vector right here. And we're going to project u onto v. So we're going to drop the perpendicular, and then we have our projection right here. That's the projection of u onto v. And there's an angle formed when we do this, which is theta. So remember, because we're dropping this as a perpendicular, there's a right triangle here. And that means that this side is involving the adjacent side to that angle. Aha, so we're going to use that. So the magnitude of the hypotenuse times the cosine of angle theta would be the length of the projection. Right? So we just take the cosine, which is adjacent over hypotenuse, which is true for any theta, right? It's a ratio. And then we want to grow it to be the size of this particular triangle because this hypotenuse is the magnitude of u long. All right, now, sure, wonderful, but I can multiply that by the magnitude of the vector v over itself. Because why not, right? I can always multiply anything by 1. I learned that a long time ago in math class, right? Okay, so we're going to multiply by the magnitude of v over itself just to make our lives fun. And then we multiply these. So this would be equal to the magnitude of u times the magnitude of v times the cosine of the angle divided by the magnitude of v. And that numerator should be setting off little bells in your head. That's a dot product, right? That's how it ties into this section, right? So this is u dot product with v. Actually, I'm going to write it over here. U dot product with v over the magnitude of v. That is the size of the scalar. And that's the formula we have right down here at the bottom of the page. Right? Okay, now what about the direction of v? Well, the direction of v is v, right? But we want to make it so that it's going in, let's put it this way, we want it to be a unit vector. So we want it to change v to a unit vector. So we're going to take the vector v and we're going to divide it by the magnitude of it, of vector v. Right? So v is whatever it is, and then it's pointing in that direction, and we're going to divide by that to make it a length of 1. Why do we do that? Well, because that way then we can put the two pieces together. If we take the direction and we multiply it by the length, right? The length is over here. That's the scalar. So u v over the magnitude of v. And we multiply that by v over the magnitude of v, right? Because v will have its, whatever way it's pointing. Right? Cosine this, sine this, whatever, right? But the key will be that once I divide it by the magnitude, that'll turn that vector into a unit vector. And then when I multiply it by this guy, that'll make it the length that I particularly want. All right. So then let's do a little bit of changing up here. This is u dot product with v over the magnitude of v times the magnitude of v. Okay, well, v's angle with itself is 0, right? So what's happening down here is you're actually taking the dot product of v with v, right? See, remember that, let me make a note over here. So note, the angle between v and v is 0, and the cosine of 0 is 1. So this is actually a dot product as well. So this is the dot product of u and v over the dot product of v with itself. And that will all turn into a scalar. That'll be a number. And then we'll multiply it by the vector v to have our vector answer. Because the projection is a vector. And there's our formula, our second formula. Right? So here's the first one, and there's the second one.